thank you very much and welcome once again for the second class. So yesterday we saw several limit theorems, and the most important property actually we had to discover was the property of infinite divisibility. I just will write down what this means. So we have some distribution mu. So once again, we are maybe on the real numbers. We have the Borel sigma algebra. After yesterday's session, we more or less know what this should be. And we have some probability measure, and mu is called infinitely divisible if for any n, so if we have a random variable which is distributed like mu, then n for any n, there is another distribution, is a distribution nu n. We will call this maybe the convolution root. So this will be, we can already write this like convolution. This is the star for the convolution, such that for any family, for an independent family of x and 1, x and n, which are distributed according to this new n, each of them. So x and k distributed to new n, such that we have that in distribution, the sum of those independent copies of this random variable with distribution nu n are distributed according to x. Yeah. So yesterday we already have seen some examples. So the easiest example was, of course, the constants. So if we have some constant in the real numbers, then the delta c was just convoluted with c over n divided to the power, convolution power of n, such that we see that it is infinitely divisible. The next example we had were the normal distributions. So if we have, so we could see this from the fact that if we have two independent normal distributions and we independent randoms with normal distributions, and we sum them up, we get another normal distributions. This means if, for example, we have a random variable x, and here we have some, so this could be, I wrote this down for the real numbers, but of course, this is also true in always in RD. So this is also true in RD. So if you have a vector, we can cut it into n equal pieces. Summing them up gives us back the vector. If you have a normal distribution with some expectation vector m and a covariance matrix A, then for any n, a family xn1, xn IID with xk distributed according to m divided by n and 1 over n a satisfies the fact that summing them up once again that we have the property of infinite divisibility. So we introduced, so we saw something, another distribution where this was satisfied, and this was the Poisson distribution. So if we have a Poisson distribution with some intensity lambda positive, then we can always find pi n ones, n, each of them pi n case distributed with intensity lambda over n, so IID, such that once again the sum is distributed like pi. Okay, so this was what we have seen. What we haven't seen, well, what we have seen in the next step was a compound Poisson distribution, and we just defined it via random variables. So what we had was a family of IID, random variables with values in RD. So now, after the last session, we know what this actually means. So, and we have an independent Poisson random variable, so that the CK are independent of those. And we defined a new random variable, C of omega, just summing up k from 1 till, now we should sum up from 0 till, okay, no, should be from 1. If it's 0, actually, then there's nothing to be summed up, of omega, of zeta k of omega. So this was a compound Poisson random variable. So this means instead of when you have a Poisson distribution, you are adding up ones, but now we just add up independent copies of a given a random variable with fixed distribution. So what we did was the calculus of the characteristic function. So I don't want to repeat this, but just to remind you what this was. So for u in RD, we calculated that this has a special shape. This was the exponential of t, and then e to the I u zeta minus 1, and here lambda mu d zeta. This was the shape which we got out. And this shape is very, very characteristic. So what have we achieved with these examples? First of all, Amit just asked the last time an example for a non-infinitely divisible distribution. Okay, I'll give you. I mentioned it, but actually I didn't prove it. So I now can give a little proof. So maybe a small interception. Example that u minus 1 is not infinitely divisible. Okay, so what you do is you calculate the characteristic function of such a thing. You have a random variable z, which is distributed according to the uniform distribution of z of u. So you have 1/2 integral from -1 to 1 I t u z dz. So okay, just calculating, you get out sinus of u divided by u. So this distribution is symmetric, and if it's symmetric, this means that the characteristic function should be real valued. This means if there are two zeta 1 and zeta 2, which are independent, zeta 1 independent from zeta 2, then this should be, they should satisfy that the square root of sine of u of this should be that we have two of those factors. Well, it's clear that these are the two factors which are the only possible ones. And of course, if we sum up two symmetric independent random variables, the the distribution should remain symmetric. This means if we have something symmetric here, we would expect something symmetric there. But of course, this object for values, for example, u greater than u between pi and 2 pi, actually is not anymore real valid. So it's not real valued. So the zeta i's cannot be symmetric. Okay, and this is a contradiction. Okay, so because zeta is symmetric, and you can see that if you have a symmetric distribution, then the factors of the convolution root should also be symmetric. So if you have two symmetric distributions, you convolute them, then they will be also symmetric. And this is vice versa. So the symmetry is preserved, and this is actually not the case here. So this is what we coming back to the main story. This is what we calculated the last time. So what we've achieved is the following theorem. So what we've achieved is the following: if we have the sum so if so I call it theorem. So if we have a random variable, x, which is the sum of 3 parts, so x with x being the sum of, first of all, a constant, plus some vector y, plus some vector z, where y is independent of z, and y is some kind of normal distributed A, and z is a Compan-Poisson distribution, so, has a Compan-Poisson distribution, z, CPP, lambda with some measure mu, then x is infinitely divisible. Okay, so this is what we've seen. Each of the components is infinitely divisible, so summing up independent parts of them are infinitely divisible. And what we get is that the characteristic function has a certain shape. So the characteristic function of x is x of some eta of u, and eta of u is very special. It has, first of all, the deterministic part. This is I u b. It has the I u b. One should I u b m plus m here. So and the mean of the Gaussian part. Then it has minus 1/2 u a u u, and it has the Compan-Poisson part. The Compan-Poisson part, e to the I u zeta minus 1 mu lambda mu d zeta. So it is a very special shape. And the question is this all? So and the Lévy-Khinchin theorem just tells us that it's almost all. So this is a theorem. I actually don't have the means and the time to prove it, but I think it's motivated at least by these kind of examples. Theorem of Lévy-Khinchin, and it tells us that we have the following repetition. for mu, a distribution on RD, well, it's true in a much more general setting, but I don't want to go into this. Then, for any k kappa positive, are equivalent following the following two things. First of all, we have mu is infinitely divisible. And the second thing is that the characteristic function of mu has the following shape. It's exp of eta, as before. And it has something very, very similar to this. It has this exponent eta, and there exists a vector b in Rd, a symmetric positive semi-definite matrix. So this corresponds to the Gauss case here. A matrix A, and we have a measure nu, a sigma finite measure. So it's not anymore. So the measure we had here was lambda times mu. Mu was a probability measure, so lambda times mu is a finite measure. So this is something we cannot retain. So this is something we will not. We'll have something more general, a sigma finite measure only. This means a measure which has we have a repetition of the space. In each part of the space, we have a finite measure, but in total, it's an infinite measure. So this is something much more general. For example, if you have the Lebesgue measure on the real numbers, on each interval, each finite interval, it's finite, but in total, it's an infinite measure. Okay, so we have a sigma finite measure nu. Well, including infinity, satisfying, first of all, nu in 0 should be 0, so we explicitly exclude 0. And we have a certain integrability condition, so integral over R or D of 1, oh, that's 1 here, kappa squared minimum y squared nu dy should be finite. So infinite divisibility is characterized by those things. This means such that, and I write down the exponent, eta of u is IBU minus 1/2, here AU, U, and then we have something which is a little bit more general than what we have here. It's the integral over RD, e to I U B minus 1, and here we have something to add, IUY, and here we have some indicator for the values that y is less than kappa. Kappa of y nu dy. So this is the characterization of infinite divisibility. So far we have seen that examples of this imply infinite divisibility, but the way back actually includes a little bit more. So what actually does this mean? What does this integrability tell us? So it tells us, first of all, we have, so this here can be decomposed into two parts. So we have something which is finite, and this is first of all for all values beyond, outside a ball of kappa, around 0, we have that, well, kappa squared nu dy is finite. So this is something, this is a measure which is positive. This is a positive constant. Plus, and here we have something which is does not correspond to a finite measure. Here we have something on the ball of kappa around 0. There can be something like a pole. So this is nothing but this condition written down here. So this here does not mean nothing else, but b kappa 0 complement is finite. So we have outside a ball, the measure nu is finite, but around 0, so this is true for any kind of kappa. So as close to 0 it may be. Around 0 we have no finite measure. So this means if you look at the measure like this, if we have a finite measure nu, if nu, then the measure should be lambda. So this means, so finite measure nu, then this is nothing but the lambda. This means the intensity. This means for outside the ball we have some kind of finite intensity, but around 0 we have something which does not correspond anymore to a Poisson process, but something with infinite intensity. So what does it mean if our nu has, for example, density? How does it look like? So if nu has the following shape, dy is nothing but, for example, 1 over y dy, 1 over y to the p dy. So what we have to satisfy is that around 0, so first of all we have the square minus p dy should be finite. Okay, and what kind of exponents p do allow this? So when is this a finite quantity? So, pardon? So, okay, p is less than 2. Okay, so p less than 2, then it's definitely finite. But there can be even a weak pole here, so this is p less than 3. So there can be poles up to order less than 1. So so p less than 3. Okay. Okay. With this, we see that there's a certain limit on the measures nu. This means there cannot be anything. There have to be finite measures outside any ball around 0, and around 0 they have to admit a pole up to a certain order. Okay, so having this, we want to discover some distributions which have not been covered yet by the compound Poisson case or the other cases, and these are, for example, distributions like the Cauchy distribution. So just a short reminder. So first of all, are there questions about this? Please interrupt me if there's something. Okay, so So, so far we had the concept of infinite divisibility. This means we have a distribution which can be decomposed into equal parts. We'll now introduce a concept which is a little bit stronger even. It tells us that we can divide up, if we have a random variable nu, according to some distribution. And what we will do is, we'll just divide it up, the distribution, into a rescaled version of mu itself. So far, for example, we had a Poisson distribution, and we summed up different versions of it. But it is not absolutely clear that the different parts we were summing up had something to do automatically with the distribution we were looking for. The next step will be to make this a little bit more systematic, and this is example of stable distributions. So when we are talking about the normal distributions, so if we have the normal distributions, for example, sigma squared, then the what we get out is that for any n, we got this yn k's, which were nothing, well, IID, first of all, yn, with the distribution where we're just 1 over n in the constants, so y n k, 1 over n m, and 1 over n sigma squared. But the interesting thing that is that this is nothing, that the distribution of y and k is nothing but this distribution of y itself with a proper scaling. It is nothing but the scaling of y divided by square root of n. So this is what we got there. Just this is correct. This okay, so we get this relation. So these distributions satisfy that summing up that yn k, yn1 plus yn n are distributed just like y. And this means, well, okay, just as I mentioned, this is nothing but just versions, independent copies. So if we have zeta n y, zeta n n, where zeta n k is distributed like y itself, n m sigma squared, then we have that zeta n, zeta, so it does not depend on n anymore. Zeta n, zeta 1 plus zeta n divided by the square root of n is just distributed like z itself. So what we get out is that if we start with random variables, independent copies of y itself, zetas, and we sum them up and multiply each of them with a constant, in our case will be 1 over the square root of n, then it's again zeta distributed. So the difference to infinite divisibility is that the parts we're summing up are now rescaled versions of the original distribution. So a typical example is, for example, the Cauchy distribution. So the Cauchy distribution has so zeta with the Cauchy distribution B gamma. It has the following density. It's like dx gamma, so pi gamma, 1 plus, and here we have some x minus b divided by gamma squared. So this is the density of the Cauchy distribution. There are several properties of the Cauchy distribution. First of all, what we have seen in the last tutorial is that there are no moments. So this, of course, x times x divided by 1 over x squared behaves for the tails like 1 over x, and for large values this does not converge anymore. So the expectation of zeta, is infinity. So we already calculated this. We have finite moments of alpha is finite for all alpha which is less than 1. And the characteristic function of zeta is also something which can be calculated rather explicitly. IUB minus B, the modulus, the absolute value of U. Okay, so this is something very, very special. And we will see that, for example, first of all, it's infinitely divisible. It's, so it's zeta divisible. The easiest case is that if zeta is 0, 1. So if we have, for any n, we take independent copies, zeta n1, zeta n IID, and the distribution is nothing but the values here divided by n. So zeta nk is nothing but the Cauchy distribution of here b divided by n and some gamma divided by n. So how can we see this? This is not too difficult. So y of n1 plus y and n of u. So they are independent. So we have y n1 u to the n. So we know what the parameters actually have to be. There are those here divided by n. So we have x, and you have n times what we have here, I u b divided by n minus gamma divided by n u. So as you can see, everything cancels out, and we have phi of the original random variable. Pardon, it should be zetas. Zetas here, zetas there, zeta of u. Okay, so it's a very easy structure. And the interesting thing is, so we have found the characteristic function, but in fact, with respect to the Lévy-Khinchin theorem, we would like to know what the measure nu is. And I will not show this at this point, but a little bit later, we'll have a look at it. So what you can show is the following, that this is nothing but e to the I u zeta minus 1 minus I u zeta, and here d zeta divided by zeta squared. So in this case, nu d zeta is nothing but d zeta divided by zeta squared. So it's a very special case. So we have some power law here, the nus. The measure nu is something which is decaying very slowly, and it's a non-trivial measure. So we found a case of a distribution which satisfies something similar to the Gaussian case. So if we have, if zeta is Cauchy B gamma, then the distributions 1 over n zeta have the distribution Cauchy B divided by gamma n. So what this means is that if for any n we take n independent copies of the original random variable zeta 1, zeta n, zeta I distributed like zeta B gamma, then summing up these independent copies, we get 1 over n zeta 1 plus zeta n is distributed like zeta. So this means the things we sum up are actually zeta 1 divided by n plus zeta n divided by n. Okay? So just in the Gaussian case, we had here the square root. So we had here zeta 1 divided by the square root of n plus zeta n divided by the square root of n here. So this means we start with a distribution and we sum up rescaled independent copies of the original distribution and we get the distribution back. And this is the motivation for stability. So the question is, questions? Please. Where are you? Exp. I. This is the characteristic function, phi of zeta. Yes, this is, well, the characteristic function is just. Yeah. So IUB. Is this clear? No, okay, I did not show you the calculation. Okay, this is the result, exactly. So, so the result is not too complicated, but it's quite some calculation. So there are several ways to do it, but one way to see it will be just something we can do maybe in the afternoon. Okay? So stability means that you have a distribution is stable if you can sum up rescaled versions of the original distribution and you get up where you started with. So, and this is something I want to talk a little bit more about. I talk about this because these kind of properties are important because they give rise to certain kind of processes, well, stable processes, and they are in applications rather prominent. So I was restricting myself to the most symmetric distributions I can talk about in this context. The good thing about stable distributions is that they have a lot of extensions for non-symmetric distributions. This is something very different from the Gaussian case. There are no asymmetric Gaussian distributions, but there will be asymmetric stable distributions. The Cauchy distribution is also stable, but apart from this, all others have asymmetric extensions. So a rotationally invariant distribution, let's call it mu on RD RD is called stable. If for any n, there is a constant a of n positive, such that for n plus 1 independent copies of x distributed according to mu, we have that x1 plus xn is distributed like a of n times x. Okay, so whenever we have this, it's called stable. This means for any n, there is a constant, such that if we have n independent copies, we sum them up, we get the distribution we have started with. Rotational invariant just means it's the strongest form of symmetry. This means for any O, which is just in D, some kind of rotation, we get that the distribution, and we have x, which is distributed according to mu, that OX is distributed like x. Okay, so this means whenever you just rotate everything around, the distribution does not change. This is the strongest version of symmetry you can get. Symmetry means that you only have, with respect to the symmetry in the origin, but this is actually with any kind of rotations. Please. No. No, it's not that you don't. In this case, you don't scale the distributions. Okay, implicitly you do, but this is written down in the sense that you sum up the copies, and then you get distribution defined by the scaling of the random variable. Well, how it scales depends on the distribution. For example, here we have the scaling of the square root, and here we have the scaling of 1 over n. So the thing is, we will just see, we'll identify an just as a certain power of n. It's n to the 1 over alpha. Once again, please. No, this depends. So, okay, we're heading towards identifying this, and if we have identified this, this will be some kind of power. Then we get some scaling, but it's not linear scaling. It can be some power law scaling in general. In the Cauchy case, we have linear scaling. We have the square root in the Gaussian case, and in other cases we have a scaling with n to the 1 over alpha. So this is the next thing we want to come up with. So if we have this, then it can be shown. Then okay, I cannot show this at this point, that a of n has the following shape. It's n times n to 1 over alpha for some alpha between 0 and 2, and it cannot go beyond this. So rotational invariant is something, a stronger version of infinite divisibility. So we can find an a of n such that if you can just see it like this, a of n. So what we have there is that we find it's a distribution to which according to which x is distributed is called stable if we can find independent copies of x. Pardon? Now, of course, we have n, and then we have x, so it's n plus 1. Pardon? So, rotationally invariant means that we have a distribution for a distribution. Means that we have n plus 1 copies. The first ones are independent. So, we can sum up these copies, and we can scale them all at the same time, such that we get back the original distribution. This is the original thing. So what we get out is just in the Gaussian case, we could sum up independent copies of these Gaussians, and we get back the original Gaussian. But the scaling here was just with the square root, and here we in the Cauchy case we had to scale with 1 over n. Here it is. So the scaling here was 1 over n. So whenever there is something like either the square root or n itself, then it's called stable. And no. So the fact that I write down rotation invariant has to do with the fact that I don't want to write novels. So it becomes much more complicated in the non-rotational, but it also exists, and it's a little bit more involved. Please. Yes. Yeah. So, okay, what we see is, so it can be shown that the only AN possible has this shape. Okay, so, and of course, this depends on the parameter alpha between 0 and 2. And this is, so this is why they're called alpha stable. And of course, what we could see is that if alpha equal to 2, then we are in a regime, we're here. So we divide by n to the 1/2. This means we are just divide by, so this is zeta I divided by n to the 1/2. So alpha equal to 2. And in this regime, we were in the regime of alpha equal to 1. So n to the 1 divided by alpha. So there are other possibilities for alpha between 0 and 2. All of them do exist. And they satisfy the following things. So there are distributions which satisfy this, and these are the so-called alpha stable distributions. So how do we identify, for example, the Lévy measure of those? So it can be shown once again. So it's an elementary but lengthy calculation that for alpha between 0 and 1, and for u positive, there's a representation of u to the alpha in a very complicated way, but which resembles very much what we need. Gamma of 1 minus alpha times, and then we have an integral I to the u z minus 1, and here we have dz z1 plus alpha. So this can be calculated in a, okay, you can see these are 12 lines, but it can be done in a very in a direct way. So, so this is in the real numbers. No, from 0 to infinity, pardon, 0 to infinity. And this can be also done for a negative, okay, this, in order to, so okay. U, so the alpha can then be written of gamma 1 minus alpha, like integrating over z, e to the y u z minus 1, dz, and here we have z to the 1 plus alpha, for alpha between 0 and 1. So there is one way to get this. When we had the normal distribution, 1 with phi, and we have some zeta. Pardon? Which one? What of this one? Or I didn't get it. Of phi. This one? Please help me. That one? Okay. So here, what's the left-hand side? U to the alpha. This is a function on the reals, yes. But this is a number. So here is also, here you see U enters. So it's a function, so it's a representation of U to the alpha. Okay, so it's a very complicated way to write down U to the alpha. And of course, distinguishing positive and negative parts, you can write it like this. And there is, so in this case, we had e to the minus 1/2 U to the square. Okay, maybe just write it like this. In the case of y being Cauchy distributed, 0, 1, we had that phi of y of u was exp to the minus u. And in a general case, so if for there exists distributions mu alpha, such that for zeta, or maybe let's call it x, distributed according to mu alpha, phi x of u has the following shape, is exp to some minus, and then we have some constant c of alpha, and then we have u to the alpha. And these are exactly those rotational invariant stable distributions. So, okay, why so complicated? The problem is that in general, for general alphas between 0 and 2, we cannot write down the densities. The densities are unknown, except for special cases for alpha equal to 2, when we have the normal distribution and the Cauchy distribution in the case of alpha equal to 1. If we have an alpha which is not in this range, so it's either between 0 and 1 or between strictly between 1 and 2, then we don't know it. There are several properties we know, but actually we cannot write down in a closed form the density. So this is one of the problems of alpha stable distribution. But beyond this, they are very well known. They have a lot of nice properties. So properties of alpha stable. So distributions. First of all, okay, as we have seen, for alpha equal to 2, then we have some Gaussian, which is an exceptional case. It's not the typical case of an alpha stable distribution. More typical is the Cauchy case for alpha equal to 1. But first of all, for alpha between 0 and 2, they are non-Gaussian. So for alpha equal to 2, mu alpha is Gaussian. So normal distribution 3. Then for all alpha between 0 and 2, which are not 1. So for all others, there are non-metric extensions. Extensions. I don't want to write them down at this stage. Maybe a little bit later. And for all alpha strictly between 0 and 2, the distributions are heavy-tailed. This means the tails. This means the probability that any random variable distributed according to mu alpha for large values of r behaves like 1 over r to the alpha. So this means they have distributions which resemble, for example, very much of the Cauchy distribution, where you also have this kind of decay. It decays like 1 over r. So if r is getting larger and larger, the mass outside decays in a certain power of alpha. So this slow decay, this means that there are still a lot of mass very far from the center, which is in this symmetric case it's 0, means that not all of the moments do exist. This means the expectation of zeta of p is finite if p is less than alpha. So otherwise it's infinite. And it's infinite for p greater or equal than alpha. Okay, so this means this is a class of distributions which is revealed via the Lévy-Khinchin formula, but which is not easy to write down explicitly, so you don't start with it in the first place. Okay, I think it's over. Could it be? Yes. Okay, so the next time, so this is everything I wanted to say about infinitely divisible distribution. The next time we'll start directly with Lévy processes and how they are related to infinitely divisible distributions and properties related to this, path properties, etc. And of course, we will rediscover all the ingredients we had here. So we have some linear drift in the first place. Then we have some Gaussian part, which will lead to Brownian motion, and we have a jump part, which is motivated first of all by the Compan-Poisson distributions and Compan-Poisson processes, and then there will be more general jump processes which are related just to these kind of distributions, like, for example, the Cauchy distribution. Okay, thank you.